Hello, this is Aykut Attar from Hacettepe University. Today's lecture is about growth accounting. So let's start very quickly. Growth accounting is basically about the proximate sources of growth or proximate causes of growth. So growth occurs through horizontal innovations, physical capital accumulation, human capital accumulation, or vertical innovations, or sometimes by the entrance of new firms. And it's an important field, important subfield of growth studies since Solow's seminal work. There's also Denison, 1961, I guess, for the U.S. economy as well. In some recent literature, similar studies are called development accounting studies as well, especially if the study is focusing on cross-country income differences. So why countries are some poorer and why some richer, that's an important issue, and what are the proximate causes of such differences is an interesting research avenue. So, okay. So some basics. Let's consider a discrete time economy. So here we typically take the length of a period as 1 year. And most of the studies, most of the simple growth accounting studies since Solow, take this aggregate production function. So what you see here is some aggregate representation of output in the economy. So output depends on capital stock, labor employed or the workforce, and some unobserved productivity term, AT. Okay. This is the Harrod-neutral technological progress. So AT productivity enters as a labor augmenting term. Okay, and typically, of course, we assume that alpha is between 0 and 1. If we use that aggregate production function to define GDP or output per worker or output per capita, we arrive at this result. Okay, so with this aggregate production function, GDP per capita or output per worker or output per capita is explained by capital per worker or capital per capita and this unobserved productivity term. Okay, so now let's define, for growth accounting, let's define the growth rate of any variable x in this way. So this is the gross growth rate, not percent. Then this equation, that representation of output per capita, allows us to write the relationship between growth rates in this way, right? Because there is this multiplicative relationship. Then the growth rate of output per capita will be explained by the growth rate of physical capital per capita and productivity. Okay? And then, since we want to decompose, we want to understand the contribution of different factors for GDP growth, we can take the logs and divide each term, each side of this equation by this term, natural logarithm of the growth rate of output per capita, and then we understand that part of this growth is originating from capital per capita, which depends on alpha as well, and then the other part depends on, so okay, there's a small typo here, so this will be ln, the natural logarithm of GYT. So in total, it will be equal to 1, of course, right? The growth literature originally focused on, since y and k are basically observed, assuming some value for alpha eventually resulted in how we can calculate the growth rate of A or TFP or Solow's residual. Okay. So we can very quickly and simply introduce human capital to this framework. Now we are writing the aggregate production function in a more nuanced way. We are saying that workers are productive because they have skills. So HT is the average human capital of workers, let's say. And then we can put AT, some unobserved productivity term, to this place in the production function. And then if we do the same exercise, we arrive at this formula now, right? So now growth growth in GDP per capita has three sources. One is again this unobserved productivity term, or TFP. The other is physical capital per worker, and the other is human capital per worker. Okay, and once again, alpha plays an important role in these calculations. So again, we can use, usually we assume that capital per worker is observed, human capital per worker is observed, and GDP per capita is observed, or GDP per worker. And then we can actually filter out AT, so what is the unobserved productivity in this economy if you observe Y, K, and H. Okay? We also can imagine models where there are firms or there are product varieties, right? So we studied such models in the previous lectures. So in most of the second generation Schumpeterian models, growth will occur through vertical innovation and horizontal innovation. So on the vertical direction of technological progress, we have quality improvements or productivity improvements. So these are going to be represented by this AT term again. And on the horizontal dimension, we have product innovations, new products, varieties, or new firms, new sectors, new markets entering the economy. So the aggregate production function in such economies, the aggregate representation of output, let's say, could look like this. And then now growth has four resources, right? Once again, human capital per worker, physical capital per worker, the number of firms in the economy, so they may exhibit some growth, at least in the short run, and then growth rate of unobserved productivity term, or the TFP term. Okay, so obviously there's one more new parameter here, so usually it depends on the elasticity of substitution between product varieties as well. Okay, so you may actually go back to the Romer 1990 lecture, the lecture about product varieties, and see the aggregate representation of the GDP in that model as well. Okay, or you can go back to the scale effects lecture. So in the scale effects lecture, we studied a similar model as well. Okay. So what do we have? All right. So these are simple models that work with the aggregate production technology, and so especially the first two, the basic model that you see here, and the one where we quickly introduced human capital, as in here. These are typically one sector models, so studies are handled very easily so growth accounting exercise is handled very easily in such frameworks. But there are of course more complicated stuff, such as the second generation Schumpeterian models, and slightly more complicated is so the idea is that if you complicate your story of economic growth in the long run, then of course growth accounting exercise you have to implement will be slightly more complicated. So I will take one example here. It is called factor eliminating technical change, and it is important because alpha, the capital share of the national income share of physical capital, historically increased. Okay, this is especially important after 1980s. And of course, there are certain reasons of this, and there's a literature focusing on this as well. But those parameters are important, and there are some theories, some richer theories, where those parameters are not fixed, but they are variables, and sometimes those variables can be chosen optimally by the firms in the economy. All right. So one such theory is Pareto and Seiter's factor eliminating technical change. All right. So the idea is that so firms in the economy actually face a menu of production functions. Okay. So let me explain that idea to you. So suppose that output will depend on capital and labor. Okay. So that's pretty simple. But now, as you see, the exponent AT is changing in time. So here, for simplicity, we are fixing A, this unobserved product term here, A bar. But then AT takes values between 0 and some alpha t. All right. So here we assume that the firm has access to all the technologies that lie in this interval. Okay. So the firm can in principle choose any AT level, which means any elasticity of substitution between capital and labor to operate. And in this particular model, the optimal choice will be the frontier technologies. So the frontier technology here is alpha t, okay? And so that's the most advanced technology, all right? Because that's the most mechanized, all right? Now the idea behind this paper, the one of the foundational ideas behind this paper is that if AT is just equal to 1, so if AT takes the maximum possible value, then this production function becomes the AK model, right? And we know that that type of a result would actually sterilize, would actually basically rules out diminishing returns with respect to capital, right? So the entire problem of the Solow model is that the model cannot explain long-run growth. And the reason behind this is that diminishing returns with respect to capital, okay? But if firms can increase AT to 1, to the most advanced technological setup, then this production function becomes the AK model. So that's the idea. So firms try to diminish, try to eliminate the role of non-reproducible factors. So it is here labor, okay? Because that's the reason. If production is completely free of labor requirement, then there's a constant tensor scale with respect to capital. Okay. Now in this model, written by Pareto and Seater, firms will direct their R&D efforts to increase alpha t. All right. So firms will spend scarce resources to increase their frontier technology, okay, so that they can choose from a larger set of technology options, okay. And here, of course, I'm not going into details of this model, but the end result is important because the end result will give a highly complicated picture about the sources of growth. All right. So this is the formula that explains the growth rate of aggregate GDP as a function of growth rate of capital stock and the pace of increase, the growth rate of alpha t term as well. All right. So that alpha t term and these functions mu and eta are endogenously determined within the equilibrium, within the general equilibrium of the model. All right. So this is just to show you that if you enrich your story about economic growth, the growth accounting exercise will of course get more complicated, but you will learn, of course, different stuff about the sources of growth within such a framework. Okay. So that's it. Now finally there is this model. So most of the time this literature, so there are basically two debates in this growth accounting literature right now. One is that whether it is capital or productivity that is more important for GDP, per capita growth, all right? And the other is that whether it is productivity, TFP, or human capital that is more important. So, okay, so these are two different debates and different people are working on this. So right now I will show you the textbook model that shows you how capital and productivity will play different roles within a Schumpeterian model. All right, so this is straight from your textbook, chapter 5, the text of Aghiona and Howitt. And the model is very simple since we also, we studied the main dynamics of such Schumpeterian models in chapter 4. So this is just a simple addition of capital accumulation within this framework. All right, now we are going, of course, back to the continuous time model. So this is a continuous time version of the Schumpeterian model. Let me just make sure of one thing. Okay, I misspoke. So this is actually the discrete time version, right? So in the original paper it was the continuous time. So in the textbook we are working on discrete time version. So that's my mistake. So time will be discrete. There's this typo there, or I mean a mistake, not just the typo. But anyhow, so it doesn't really make a big difference for our discussion. Now the aggregate technology is written in this way. So this is the final goods sector. And we are normalizing labor to unity, so labor is fixed. That's the production technology we saw in chapter 4 Schumpeterian model. So there are product varieties, line, located within the 0-1 interval, and each product variety is associated with some productivity level, and outside entrepreneurs try to invent more productive versions of these intermediate inputs so that they creatively destruct the existing monopoly, so they become the local monopolists that produce such intermediate inputs. Now, one important difference with the model in chapter 4 and this model is that now firms, the firms that produce intermediate inputs, they will use capital stock, capital goods to produce intermediate inputs, okay? So for this reason, profit function will look a little bit different with the real rental rate of capital appearing here. Okay, so this is the profit function of the local monopoly that produces product variety I in period T, and the cost is associated with the capital good purchases. All right, so to produce XIT units, the firm needs XIT units of capital. For each unit of capital, the firm pays the real rental cost. Okay? So, we know how to solve this problem very quickly, very simply. So, that optimal amount is proportional to the productivity of it, as we discussed earlier. And there's also, of course, there is this labor term here, but we normalize it to unity, as you know. But then this is again the inverse demand, because the optimal level will be decreasing in the rental rate, okay, because it becomes more costly. If we look at the capital market equilibrium in this economy, KT would be the total supply. I will be talking about that. That will be originating from the supply decisions of households. And XIT summed over 0-1 is the total demand, right? Because each firm, for each product variety, XIT units are demanded. So in total, this is the demand. Now, if we put XIT from this here and do the math, we arrive at this. So here, once again, AT is the average productivity across product varieties. Okay, so that's key. If that's true, now we create this new variable, kappa T. All right, now kappa T is the total capital stock of the economy divided by average productivity. All right, so it is productivity normalized capital stock level in the economy. All right, so it is slightly different than, so we usually in the Solow model and in neoclassical frameworks, we usually divide total capital stock by labor. Okay, now we are doing that with average productivity, and you may actually imagine that L is here as well. So L is just equal to 1. Okay, now if this is true, if we define this and if we use that aggregate result, okay, that result originating from capital market equilibrium in the economy, we can solve for the rental rate as a function of kappa, and then we can also solve for XIT as a, we can write XIT in this way, and then output in general from the final goods sectors will be written in this way. Okay, so with respect to the discussion on growth accounting, you can actually use this equation by replacing kappa. You can actually use this equation, and eventually you arrive at this one, something like this. Okay, so growth in GDP will be originating from capital and will be originating from productivity. All right, so at the aggregate level, we are still dealing with the same economy. But of course, the model that we are now studying is much more complicated from a microeconomic perspective. Okay. Remember that once we know this, we can write profit. Okay, and why profit is important? Because there will be innovators, and innovators will be looking up to the future profits that they may obtain, right? Remember that part of the story of the Schumpeterian model. So we had the success probability. Success probability depends on normalized R&D expenditure. Okay, so normalized R&D expenditure is here, NIT, and there is this targeted productivity in that sector I. So if you do the math from this model, I'm not just doing that, but you should with pen and paper, you find the growth rate of productivity. So this is the growth rate of average productivity in the economy. Now in this model, that productivity depends on kappa T. All right, so remember kappa T is total capital stock divided by average productivity across product varieties. Now what is happening here? So if kappa is going up, growth rate is getting larger. So what's the reason behind this? The economy is getting more mechanized. You have more capital stock. Rental rate decreases. When rental rate decreases, optimal amount of product variety, XIT, increases. That increase creates an incentive. So that increase creates higher profit opportunities. And then for this reason, RIT, the total research expenditure, increases, and then that creates a higher productivity growth in the economy. All right. Now, in this equation, you have two unknowns, G and kappa, right? Because we have to solve for kappa as well. So remember that I told you in the capital market equilibrium discussion, I told you that KT is the total supply of capital. Okay. Now, where is this coming from? Initially, it is given, but then there is this saving rate, S, which is between 0 and 1, and there is this depreciation rate. This is pretty much the, good old capital accumulation equation. And capital accumulates through that, right? So what happens then? That equation describes the growth rate of aggregate capital, all right? And from that, we want to basically focus on the growth rate of kappa, right? Now, in a steady state, from this equation, you realize that in a steady state, kappa must be constant, right? Otherwise, G could always grow or G could always decrease, okay? We don't like that. That's not the type of steady state we can construct in such models. So just from this equation, we understand that if we want a balanced growth of GDP per capita in the long run, which depends on productivity growth rate, which is G, we must have constant kappas. What is constant kappa? So growth rate of capital stock at the aggregate must be equal to the growth rate of AT. But growth rate of AT is itself G, right? So in the steady state, we must have this property then. The growth rate of capital stock must be equal to the growth rate of productivity, average productivity. Now, what is that growth rate? Growth rate of capital stock. That comes from capital accumulation equation, right? So if you divide both sides by KT, you got this, and then you replace YT from this equation, okay? YT is depending on productivity and kappa itself. So you have this, but realize one thing. AT divided by KT is just kappa T to the minus 1, right? So this growth rate at any T is equal to this. Okay? So be careful here. So growth rate of capital stock at the aggregate is equal to S times kappa T to the alpha minus 1 minus delta. Delta is the depreciation rate. Okay? Then we have two equations and two unknowns, right? The first equation is the growth equation. Growth rate at the steady state depends positively on growth rate, the steady state value of kappa, but then the growth rate of productivity also must be depending on kappa as well, the steady state value of kappa. So if you solve these equations, you can find, explicit formula for G and explicit formula for kappa. And graphically, you see the result here, okay? Now, that's an interesting result. So what is happening here? Let's do some comparative static analysis. If S is larger, if society starts saving more, then that's good for both kappa and G, right? Because that blue curve here, which is this one, shifts upwards. So a new equilibrium, for instance, could be occurring here, all right? Because S will not be affecting this. If you do the math, if you find this function, you will realize that it doesn't depend on S. So when S goes up, the society saves more, accumulates more capital in the steady state relative to productivity, average productivity, but also growth rate will be larger as well. Okay? But you can also imagine things that increase research productivity. For instance, if lambda is getting larger, research is more productive, so this curve shifts up, okay, through here, for instance, and then the society in the long run grows at a higher rate, but then with a lower capital stock per average productivity. All right, so these parameter changes then create different long run equilibria. Okay, and in these different long run equilibria, the share of growth originating from capital capital accumulation would be different than the share of growth originating from, of course, productivity growth. All right, so those parameters are then very important in understanding what are the different contributions of capital accumulation versus innovation in such slightly more complicated frameworks. Okay, I want you to read the text because chapter 5 introduces some empirical material to you as well. So why are these theories important? So that's a good question. So why do we care about these mechanics, right? Because they have some empirical implications, and they have some they provide us some provide us with some good insights about how to understand the proximate causes of growth in the real world. Okay, I will not spend much time on the debates, surrounding around the share of human capital, but there is this essential reading that I posted online, so you should check the website of the course to see that reading. That's a nice recent paper that summarizes the role of human capital in understanding the development differences across countries. Okay, so that's all for this lecture, and thanks for watching.